So today, here's some 304 stainless steel 14 gauge wire, and I've measured out to about 10 feet, and this is for a project, I'm gonna see the resistance of it. So this is a little ditty I made when I was I think, Pro Mariner a long time ago. I don't remember how it works, but it's a wire resistance calculator. So you can put in the gauge, here are your inputs at the top, the resistivity, so you have copper, it's 1.6, annealed, it's 1.7, aluminum's 2.6, tungsten, 5.6, stainless steel, 7.2. I think there's a multiplier of 10 to the negative seventh on there. But it's not actually, it's a very, very small number. These are multiplied up for the equations. So it takes the resistivity and the thermals, and it will tell you stuff like how long you have till it melts, the steady state operating temperature, all based off of the current and voltage and gauge you have. And the coolest thing is it spits out the length right here in feet. So I'm going to put 5 amps of 14 gauge stainless steel at a voltage of 0.53 volts. So if I put 0.53 volts and this works, and 5 amp, we should see 5 amps go through a 10.05 foot segment of this cable, and it would be about 106 milliohms. So, or 106 ohms. This is very cool. Let's see if this works. Let me show you. If you increase the gauge, say 22, you need much less distance because there's much less wire, so it doesn't more resistance, less material, right? And if we change it to copper wire, you can see you need a lot more material to emulate the same power and resistance. So, and you can change the voltage up and that does stuff too. So let's test it out. Measured out to 10 feet. So we'll grab you right here. Thank you. All right. So the Excel calculator did work. It worked once. Maybe this stainless steel stranded wire is much smaller than 14 gauge because it's only exhibiting 200 milliamps. There's the voltage. We could be seeing some resistance from the terminals here. These aren't really crimps, these are just alligator clips. All right, I thought of a way to test this, whether the power is getting reflected at the connection points or not. We'll dump 5 amps through this 10-foot length of cable, and if it is 14 gauge, it should only reach a steady state of 62 degrees Fahrenheit plus ambient. Well, that's kind of hot actually. It's like a couple hundred degrees. Anyways, but say it's like 20, it's going to get much hotter. So this is an exciting experiment. Don't worry, I need to replace the floor as it is. So, but that is hot. Not too hot, but very hot. These guys. Whew, these are very hot. Doesn't make sense. I have an idea. If it gets too hot, the resistivity will change and mess the whole experiment up. So I will measure the voltage between these 2 points with my multimeter, and that will give me the voltage across the wire. And if we know the current, that should see what's really going on. See if there's very small voltage drop across these connecting points, we know it's really the wire's resistance is totally different. If there's a large voltage drop, most of the power is bleeding off at these connection points and not even making it to the wire. We will see. All right, I did it. There's a voltage of 1147, 11 volts and 11.47 volts, and that was at a current of 5.1 amps. So in reality, this 10-foot section of wire is exhibiting a resistance of 2.294 ohms from measurements, and you can take the voltage over it divided by the current through it, gives you the resistance. Pretty cool. Now I'm pretty sure the gauge is correct because I bought it, and the diameter, say it's 1/16 wire, gives us a diameter of 0.062 inches. 14 gauge is 0.064. Okay, so it's a little smaller. So here's 626, and this is 14.2 gauge. So it shouldn't make a difference, but because it's stranded, that maybe affects it somehow. Interestingly, if you take the resistivity and multiply it by 10, the answer appears to only be off by a factor of 2. That's a pretty perfect. Maybe I messed up somewhere and I have an extra multiplier by 10 floating around in here. Or when I copied this constant n from Wikipedia, I messed up the powers of -10, and instead of 10 to the -7th, I said 10 to the -6th, or other way, 10 to the -8th. So really this could be 72. But still, there's a 2. There's a factor of 2 floating around. That's peculiar. So this steel wire really exhibits a resistivity of 149, which is a lot more than 7.2 or 72. But that's a math. I always rather take information from real-world experimentation. So cool. I hope this was interesting, and stay posted. I have lots of Excel calculators on lots of interesting things. I get really into something, and then I make them, and then I forget. Like, yeah, there's some equations in here. And we have the thermal capacity over here too, so it tells you how long it takes to fill up with joules in a vacuum with no heat transfer. That's what the seconds thing is. And then, yeah.